So I'm sure you know the Fourier transform in one dimension. So what it says, the Fourier transform, is that any signal can be decomposed as a sum of sinusoid signals. So, for instance, you have this step function here, and then you can reproduce that step function by adding many sinusoids. So you have, so it has kind of main trend. So this main trend you reproduce with a sign that approximately has the same period. Okay, so period, because you know the Fourier transform assumes that the signals are periodic some way, and what it does is that it replicates this signal infinitely many times, and then you have the periodicity, and then you have a main period. So you have this main period, but it doesn't. So it looks like, but it is not just the same signal. So you need to add smaller and smaller sinusoids. And these smaller sinusoids, so here you have the second sinusoid that you have to add, and then all of them. For each one of them, you have to control what is the amplitude and what is the relative positions, whether you should shift them to the left or to the right. So the amplitude is the amplitude of the sinusoid. The period is the period and it is related to the frequency. Tomás, contanos un chiste, anda.
Va uno y le dice, me ha picado una serpiente, cobra, no gratis.
So, and then the relative position is the phase. Okay, so in general, when we write the signal, we have these three things that we can control. So I will write it in continuous phase, continuous time. So you have an amplitude, and then you have a frequency and a phase. So the frequency, this one here, is 2 pi over lambda. Okay, so lambda is the wavelength, and omega is the frequency. And so the three things that you can control are the amplitude, you can control the frequency, and you can control the phase. Frequency and wavelength is the same, okay, so they are related. So frequency and wavelength, they bring what is the separation between peaks. Okay, so there are again some things about what happens with discontinuities and these things, but we will not take care about them. So those amplitudes and phases and all that. So yeah, so here what we have is that the more space you add, the more sinusoids you add, the more similar you are to the signal you want to produce. By the way, why do we have these oscillations? How are they called? Ripples, but these ripples occur particularly in this signal because of something. Because? No, interference. Because there are discontinuities. This is a step function. So it goes very quickly, just one sample from high value to low value. So discontinuities causes these ripples, and they are called the Gibbs effect. Have you heard about that? Gibbs effect. So this is the Gibbs effect. And it is because of the discontinuities. Jaime, cuéntanos un chiste, anda.
Va un caracol de ropa. Muchas gracias. Para la bola que atropellé tampoco.
Okay, so yeah, so these are the main components that we can control. I think it's the same equation. And then, how do we find these coefficients? And for that, we need to introduce the concept of inner product. Okay, so let's from the slide, let's think of sigma. Okay, so that to keep things very small, I will only talk about discrete signals, and well, let's say that I have this signal. This is x of n. This is n minus 1, so it goes from 0 to n minus 1. And in this case, it's 4. This is 3. So, and then as we said before, the Fourier transform assumes that this is periodic. So now it repeats the same signal infinitely many times. Okay. Goes this on the other side too. So on the other side, look like this. Like this. Okay. So it is repeated many times, but there is a central period. This is the central period that is repeated. Okay. And we know that the Fourier transform of the discrete signal. So my discrete signal goes from 0, 1, 3. I know that the Fourier transform is a signal. I will use this notation here. And it also has 4 coefficients. So if this has 4 coefficients, this one also has 4 coefficients. Okay, but we know that there is a concept of frequency. That this index here, each one is associated to a frequency. So each one is associated to a frequency, and this frequency is 2 pi divided by n times k. Okay, when k takes the value 0, 1, 2, 3. Okay, so now what is the formula? Formula we transform something like this. So it is the sum. Now we use this one like this one better. So here is k, but here I'm substituting by omega k. So, and then I have to add over what? So what is this index that I have to sum over? I have to sum over what? There are only 2 possibilities, time or frequency. I have to sum over time, or I have to sum over frequency. For time. Okay, so if you sum over time, you go from 0 to 1. So you are going from time frequency. So the result cannot depend on it. So you have to sum over time. Then the sum only depends on frequency. Okay, so it does not depend on it. Okay, so using this, what we can do is we can compute this x of 0, x of 1, x of 2, x of 3. No more, because we have only 3k or 4k's. Okay, and then I can rewrite. Okay, so let's explicitly write that. Okay, so what is for k equals 0? So for k equals 0, omega k is 0. And then the exponential of 0 is 1. So this is 1, 1, 1, 1. What about the next one? So the next one is exponential of j. There is a mistake here. There is a minus. Okay, so it is. So the first one is, so it is the product of 2 pi over n times k times n. But for this column, all this column, n is 0. So all of these are 1, 2. Okay, what about the next one? This is minus j. So it is minus j, then omega, I'm computing k equal 1. So this is omega 1 times n. Okay, so n for this column is 1. So this is 1 of the time. So this is minus j omega 2. This is a minus j omega 3. Okay, and the 3, 1, 2, 3 are these frequencies there. What about the next one? It is the same, but now n is equal to 2. So this will be 2 omega 1, 2 omega 2, 2 omega 3. This will be 3 omega 1, 3 omega 2, 3 omega 3. Okay, now, what does it look like? So you have a signal. So you have a signal. Let's say use also. So you have a signal x of a that you can represent as a vector. So I will use this notation, or we can use this notation. So you have the vector in real space. Here you have the vector in Fourier space. And then you have a matrix in between. Do you see? So Fourier transform is nothing more than a change of basis. From which basis to which basis? Okay, so it is basis. So let's talk now about basis, and we'll come back to signals later. So what is its basis? Okay, so when you write, for instance, you write vector x, y, z. Okay, so what you are doing is you say my vector is this one. So what you are saying is that this is x times the unit vector x plus y times the unit vector y plus z times the unit vector z. So this coordinate axis. So what we are saying is I have a vector given by these unit components. Then I'm here, this is my coordinate x. Okay. So what we are saying is I have some coefficients in front of a basis. So now this is my basis. This is my basis. These are your bases. Okay. So this is what you're saying when you write this. And what about the signal? So if I have this signal, here, let's say I have, let's make it only with 3. Okay. So what I'm saying is I have this signal, and then all the others are 0. So what I'm saying, let's put numbers to this. So let's say this is 2, this is 1, this is minus 1. So what I'm saying is this is 2 times delta n plus 1 times delta n minus 1 minus 1 times delta n minus 2. This is what I'm saying. So now these are my bases. So this is my basis. And these are my coefficients. So the signal is another vector. Actually, this vector, we can write it in general. We can write it. So in general, how can you write this? So in general, so if instead of calling them x, y, z, call them E1. So the first vector, second vector, the third unit vector. we are saying here is that the vector is the sum over all elements in your basis of the coefficient that goes with that basis times your basis. How can we write signals in the same way? So you can say x of n is a sum over all my bases, or all my bases I, of a coefficient that goes in front of my basis times my basis. So this is the same what I'm doing. So these two things have the same structure. These are my bases now. These are my bases. These are my coefficients. These are my coefficients. What about the Fourier transform? Fourier transform. Go back to here. Fourier transform has also the same structure. So it has the sum. So this is a coefficient. Okay. So this is the Fourier. This is the Fourier transform. Fourier transform. What about the inverse Fourier? The inverse Fourier transform. That's what I did. So I write it this way. So let's say is that x of n is the sum. Now I have to sum over the frequency of the Fourier transform times. Now I have the same structure again. I have some coefficients. I have some bases. So what is the difference between these two things? So here, my basis, that functions. So all of these are these functions here. So let's write the first. Let's draw the first basis. So this is the first basis. So this is delta n. This is my first element, my basis. So this is the second one. So the second one is this one. This one here. And so on. Now my bases are complex value functions, but they will. I cannot draw them as easily as here, but I can draw the real part instead. So I can draw the real part because they are complex value functions. So I can draw the real part of this thing, and they will be kind of signs. Okay, so the real part is a sign. Actually, we know what the real part of this is. It is the cosine. So it is a cosine. And the same for the imaginary part. So my basis function now is complex. But apart from that, it is the same as we are doing all the time. Okay, what next? Okay, so then this is a change of basis. So I'm going, do you remember yesterday that, or 2 days ago, that we made a change from RGB to HSB, and we reasoned that that was a change of basis. So now it is another change of basis. We are going from the basis of deltas to the basis of complex exponential. And here it is very easy to see. Okay, so in general, if you have a basis, you have an orthogonal basis. You have an orthogonal basis, orthonormal basis. So let's say that you have these bases, the E1, the EI basis, and you have a vector R. What are these relations? How do I calculate those? This is a result from algebra. It is the inner product between the vector that you are representing and your basis. So linear algebra, we have is that any vector is x, y, EI, and EI. And for that, you need a couple of things. So this is true only if the set of your bases, this one, this set is orthonormal. Okay, so what is orthonormal? It is orthogonal and normal. Okay, so what is orthogonal? They are perpendicular. So what is the meaning of being perpendicular? The inner product is zero. So two vectors are perpendicular if their inner product is zero. So for any pair of elements in these bases, this is zero for all I and j such that I is zero. So if you take any two elements in my basis and I compute the inner product, they have to be zero. And then this is ortho. Okay, so this is ortho. What about normal? What does it mean to be normal? The module of what? Of the vectors in the basis. Okay, so if I now take that, actually this is, I will write it as well. So the norm of E1, EI, that is the square root of EI, this is 1. From I on I. Okay, so for any orthonormal basis, this is true. Okay, so now it means that we need to define what is the inner product between vectors. So for instance, if we are in real value vectors, so my VI's, my vectors, generally belong as 3. So, and I want to compute the inner product between E1 and E2. So this is the sum of E1 x times E2 x plus E1 y E2 y plus E1 z E2 z. In general, this is the sum over all components of the vector. I will use a different letter. Let's use k of EIK times EIK. Okay, what if, that is, if my vectors are real? What if my vectors are complex values? I want this one. My vectors are complex values. How do I define an inner product? So it's the sum, the product between a couple of vectors, with the sum of all the components of EIK, EJK complex. This is a proper inner product. You know that to be an inner product, a function must fulfill a number of conditions. We can check those conditions. What are the conditions for being an inner? There are a number of conditions that product space in the product here. So an inner product is an inner product if all these conditions are fulfilled. So, and these are the standard things that you are using. But now, if you can define a function that fulfills all of these, then it's an inner product with the vectors that are interested. And for real numbers, this is a correct inner product. For complex value vectors, this is a correct inner product. Okay, so now, yeah, so this is fine for discrete vectors. So vectors that we can have a finite number of samples. What about if I have functions? But we know that we can define the Fourier transform. So we have said the Fourier transform, the discrete Fourier transform is a change of basis, and we have defined inner products and these kind of things. Yeah, actually, by the way, we can go back to here. We can see, okay, so what is my Fourier transform? I can find already one. Here it is. Okay, so let's see if this is an inner product. It's an inner product. Then I should be able to find it as the product of this one and my basis function. So this is x of k. This is the inner product between your signal and your basis function. And because for complex value signals or vectors, we have defined this complex, we have used this complex conjugate here. That is why we get this minus here. It's the complex value. It's the complex conjugate. This. You see, but it has the same structure as an inner product. And we go to here, and then what we see is the same structure as we had before. So this is the sum over all your elements in your basis of the inner product between x of n and your basis times your basis times your basis. So get to this there. So then having a space times your basis. But it has the same structure as we had here. Is this one. So for discrete value signals, this is very nice setup. What about we know that we have Fourier transform factor. So I can take x of t and I can compute the Fourier transform of this one. So I can do that Fourier transform. So actually, yeah, no, I want this one. So that one is for discrete signals. I won't use this one. This is the notation we have used for the continuum. Okay, so I can do that one. So, but then I need an inner product with a couple of functions. So if I have a couple of functions, what I think, I need to define the inner product between these two. What is a proper inner product? So it has a lot of varieties, but for non-periodic signals, I can define this as y conjugate and it has the same structure as this one. So summing and integrating is the same. And then have the same structure of what else I do. Okay, so then what is this one? So this one, if I follow my rule before, so it should be the inner product between my signal and my basis. What is my basis now? Is AJ omega. So this is the inner product. Actually, this is the integral that you calculate when you do that. Okay, so then how do I do the inverse Fourier transform. So I want to compute the inverse Fourier transform. By the x of t should be, sorry, not the sum, but the integral. Integral over all my bases. Now the frequency basis. We will integrate over omega. So this is summing over your bases. And what do you have to sum? I have to sum my coefficients. My coefficients are these ones times my bases. I have it. So this is the inverse for it. There are a lot of details here. So these bases are not normal. So if I want to make them normal, I have to divide. How do you make? Let's say that you have a set E1, 2, 3, that is orthogonal, but it's not normal. How can you make it normal? It's very easy. You simply have to divide by the norm of each one of them. So I divide by this one. Now it is normal. So it is also normal. So you may remember that in the Fourier transform, there are some coefficients in front, like 1 over 2 pi. And you understand where the 1 over 2 pi is coming from. It's coming from the norm of each one of these bases. Okay, good. Then, what else? Yeah, so now we have seen the Fourier transform of one the signals in a different way. So let's come back to our slides. So we need to define inner products. And this is for periodic signals. So for periodic signals, you go from minus lambda half to lambda half. You don't go from minus infinity to infinity. But all the other things, they are the same. And here we see, for instance, how these inner products can be calculated. So let's say that you have this function f, you have a function g, that is the blue one, and you want to compute the inner product between the two. So the inner product between the two, you have to take one times the other for all time points. I have to complex conjugate one of them, but this g value function, so the complex conjugate is the same. So I compute, here it is in red, the product between the two, and then you integrate over time. So it is all this area having there. So when you say that two signals are orthogonal, it means is that this area is 0. Doesn't mean that the product of the two is 0. So the inner product is 0, but point-wise, it is not 0. The integral of that is 0. Okay, so then, so you can do it with as many functions as you like. This is all the time the same. Simply, it is explaining that my complex exponentials are made of a couple of sinusoids, so cosine and sine. So this is the same that I have been explaining. Okay, good. Then, in general, these integrals here, an inner product is an integral. So this integral will be complex or real value functions or scalars. So for a particular omega, it is a complex number or it is a real number. It's complex because you are integrating a lot of complex things. So at the end, the result is complex. So you are integrating and adding is the same. So if you add a lot of complex numbers, the result in general will be complex. Okay, and what else do here? So if it is complex, then in general, I can express it in its polar form. So the polar form has an amplitude and has phase. Okay, so I'm going back to already to things that you know. So let's say that I have x of t that is a real value function. It's all for all t. This is the real number. I compute the Fourier transform, and then I have this one. And because this is real value, what is a property that the Fourier transform must fulfill?
That is the orthonormal.
No, the Fourier transform doesn't have to be orthonormal. The basis of the Fourier transform has to be orthonormal. So the complex exponential have to be orthonormal. But this one doesn't need. Okay, so if this is real value, then this is real. No? This Hermitian. Hermitian is, this is the word. So that means that J of omega is equal to X of this conjugate. This property you know, right? Okay, so what does it mean? So if I plot these numbers, so these are all complex value numbers, so I can, now this is my basis. This is my basis omega. So this is an index through my basis. And then I have a value here and I have another value there. So I have a particular frequency. And this relationship must hold. So whatever number I have there, here I should have x of complex conjugate minus. So if I have a number there, at this point, at this point, what I should have is this one. This one must be the complex conjugate of that. Okay, so if this is some amplitude and some phase, this is what? Same amplitude minus that phase. So the amplitudes are the same and the phases are the opposite. Okay, so now, why does it help? Because let's say that you will do the inverse. Hacer caso. Okay, so I do the inverse Fourier transform. So I do the inverse Fourier transform. So I have to go from minus infinity to infinity. All my Fourier coefficients times this one. This one. Differential of omega or t. So when I'm going from the Fourier to the time domain, I have to integrate over omega over frequency. This is very important in the formulas. You have to use the frequencies and time in the right places. If you don't do it, those are serious mistakes. Okay, so I have to add all these numbers, but I know that for every number that I have for a positive omega, I have the same number in the negative omega, that is the complex conjugate. So I can separate this into parts. I can separate from minus infinity to 0, and then the integral from 0 to infinity. And for every point here, I have the equivalent in there. So also what I can do is, okay, I will do a simple integral only from 0 to infinity, but now I will exploit that thing. So I have, I will use, which one? I will use this one. So for every amplitude that I have at the frequency omega, I have this phase. And this is multiplied by e to the g omega times. And I have the same one. I have the same one. But now with negative phase and negative frequency. Then I have to integrate over time, over the frequency. You see, for every number that I have at the particular frequency, I have the same number but complex conjugate at the negative frequency. So that means this integral and this integral are the same, and this depends on frequency. This depends on frequency. So I can take the amplitude out. Take the amplitude out. So the amplitude depends on the frequency. And what is this? This is twice the cosine of omega t phi. So something that was complex, a complex integral in general, only for real signals, I can decompose it as something that has an amplitude, has a frequency, has a phase. Okay, very good. So yeah, he explains things in different ways, but all the formulations are equivalent. You see, they are using the same kind of stuff as I'm doing. So this is the amplitude, these are the phases, and so on. So he's using the same kind of stuff. Yeah, this is very interesting. So, for instance, this is how we hear. So, how you hear, because there is a wave that is that arrives to your ear and moves your tympanum back and forth. And then if you plot what is the displacement of the tympanum, you can make this kind of plots. And now you can do the Fourier transform of this. Okay, so what do you think we are more sensitive to, the amplitude of the Fourier transform or the phase of the Fourier transform? So this content and this content, so explaining things in the Fourier domain and explaining them in the real time, they are the same. They have exactly the same information. Okay, so now if we go to the frequency domain, what are we sensitive to, the amplitudes or the phase? Amplitude. Yeah. So we can only hear amplitudes. So there is a very funny experiment. You can take any sound signal. You do the Fourier transform, you completely shuffle the phases, and then you come back to the real space and you hear exactly the same. So we are only sensitive to amplitudes. We will see about images later. Okay, so yeah, this with Fourier transform is the same explanation we have done before. Okay, so now we have to extend, all this is 1D still. Now we have to extend all this theory that we have to develop for 1D signals. We have to extend them to 2D signals. Okay, so what is, let's come back. So what is the basis function in the Fourier space? Actually, before we go to 2 dimensions, let me finish with something. So when you go from time Fourier space, you have said, okay, the basis here is the complex exponential. So it is the set for all omega of this kind of functions. What is this? What is the basis for x of t? We saw them with discrete signals, the delta functions. So this kind of t. So they are delta functions that are displaced to any. This is sine, this is delta t minus v naught minus t. Okay, this is a delta function. Actually, if this is the main basis, I should be able to write this function as a sum of these kind of things. Okay, so x of t should be the integral, because we are going over from minus infinity to infinity. So for all the deltas of what? Okay, so should be the inner product between x of t and my function delta t minus t naught, and I should integrate over what? Over time, over t naught, over anything else. It depends on time. So if it depends on time, I cannot integrate on time, because then I would remove the dependence on time. I have to integrate over my basis. My basis is indexed by t naught. What is this? The inner product between these two. X of t. So it is the value that you have when you have a signal like this. It is the value that you have there, t naught, times x of t times delta t minus t naught. And you have to integrate many kind of these values. Should be the right symbol should be a variable. Okay, so time for a break, and after the break we will extend this to 2 dimensions. Yeah, so we are here. This is our basis function. This is our set of basis functions. And now we have to take them in 2 dimensions. Okay, so what's an image again? So an image, let's make images. Okay, so an image is a function of x and y. Then I will have axis here, y and x. And then for every value here, so for every location, I have a different value. So this is the equivalent. It's the equivalent of my x of t. This is what I want to transform. If I want to transform x of t. So what are my bases now? My bases in real space will be delta functions again. So it is delta functions that go out, so that I can express this as an integral. It's an integral, now a double integral, over all spatial locations of the image at that location. Let us do it x naught, y naught. So the image at that location times the delta x minus x naught, y minus y. It has the same structure as this one. Okay, so I integrate it over my basis function. My basis functions are deltas. then there is a coefficient. And this coefficient is the amplitude of the intensity of the image at that location. Okay, so now in real space, my basis functions are these sets of x minus x naughts, y minus y naughts, for all possible x multiplied. So this is my basis in real space. What is my basis in Fourier space? So let's try to expand these to more dimensions. So probably I want complex exponentials. And this is omega times t. So only that now I have two time dimensions or spatial dimensions. So probably I will also want a couple of frequency dimensions. So I will write omega, but now omega is a vector, times space. And space is now a vector. And I have for all possible frequencies. So now my for all possible frequencies. Sorry. No, that's. Okay, so now if R is a vector that is xy, now my frequency vector will have two components. One is an x frequency and a y frequency. And this inner product is simply this inner product here. So the inner product between omega and space is omega x plus omega y. So now my Fourier transform looks the following, looks like this. So I have an image. We're for today. So I have an image at a particular location, and I want to compute the Fourier transform. So it's the Fourier transform at a given frequency. And now my frequencies are vectors. And this will be what? It will be the integral, and we will come back to later to over which area, over which value of my image times my frequency, my basis. Now, I will do it in 2 steps. Now, steps. So, as before, this is the inner product of R and then my basis. And this is now double integral of I R. Now this conjugate. And I have to add over, I have to integrate over what? Omega.
Perdón.
No pasa nada, apuntando ya.
Vale. Si los zombies se deshacen con el paso del tiempo, ¿son biodegradables?
Yo creo también.
Claro.
Había un pollito que respiraba por el culo. Se sentó y se murió.
Okay, so I have to integrate over what? Over. I want to have at the end a dependency of frequency. So I have to integrate over time or space. To integrate over space. So this is my inner product. Okay, and now I want to do the inverse Fourier transform. So now I have these coefficients. My coefficients have been today blue. So these are my coefficients. I want to reconstruct my image I want to do the inverse Fourier transform. I want to do the inverse Fourier transform. So I have to integrate all my coefficients. And now times my basis. But these are vectors. Now times my basis. But my bases are like this. Now I have to integrate over frequency of time. Frequency. Integrate over frequency. So now this is the inverse Fourier transform. Okay, so now what does it mean to have? So we have extended, and we have extended our basis to multiple dimensions. This is my extension. This is my new basis in Fourier space. Or this is the basis that defines the Fourier space. Okay, so but now then, how complex, two-dimensional complex exponentials look like? Okay, so here it is the same, but I have instead of using, I have used omega 1, omega 2, or omega x, omega y. He's using 2 pi u1, 2 pi u2. But u is the frequency. Here you have the same kind of stuff as written. This is the same, but now for discrete signals, I have explained because I think it is easier for continuous images, but we also have discrete images with pixels. So the equivalent of pixels is this kind of stuff. So is this one here. So we have it. See better. We started at the beginning of the class making this kind of resonance. So what if I have discrete signals like this one? So this is the 1D discrete signal. The equivalent to the image is the one with pixels, the one that we only have values in a discrete lattice. Okay, so I have these 4 values, then I have the value everywhere. So this is the equivalent of this. And what I have written before, when we have gone to continuous images, here, these are the equivalent of the continuous signals. Okay, and then if you have discrete images, you have to discretize your frequencies too. So it is the same as I was writing before. Remember, I was using 2 pi over n times an index. So here it is the same structure. It's 2 pi over an index times an index divided by the size of the image data. So if you have an image that is of size n times n, so you will have 2 different factors there. It is the same that we have done before. Okay, so then what else? You have to define the forward Fourier transform, the inverse Fourier transform, and now we recognize the forward Fourier transform, that is this one. It is the signal products that we have defined before, and the inverse Fourier transform is my coefficients times my basis, and I have to integrate over all my bases. And if it is a discrete image, then instead of having integrals, I will have terms. And then instead of continuous frequencies, I will have discrete frequencies. Right? It's all the time the same. Okay, then what else? What is also very important? How does a complex exponential look like? Okay, so let's discretize our stuff. So I have explained it here with continuous frequencies, let's make them discrete. Okay, so if they are discrete, I will go here. So I will go here. So now our frequencies are discrete. And so I have a discrete set of omega. So I will have omega k, and it's a vector. And then you have what is there. Now, what is omega k? So omega k is a vector. It has two components. And omega k x and omega k y. And which are those? So it will be the same as we had before. What was before? 2 pi over n. N was the length of my unit signal, the one that was replicated. But now I have 2 dimensions. So it will be an x, n in the x dimension times I, let's say, times I and y times j. And this is not good. This is not good because I'm not using k. Okay, so let us use k. So I will have a couple of indexes. I will have place this one. I want to place. I need to place this one. So I will write k x k y. So now we have also k. K again here is a vector. Okay, so what are our kx, ky? 0, 1, and it is 0, 1. This is my set. Okay, so how do they look? They are complex exponentials, but I can define this is the same. Okay. Instead of using kx, ky, is using v and u, r and c, number of rows, number of columns. These rc, small r and c, are the x, y's of my population. Okay, so given a frequency u and v, so these are the indexes. Okay, so these are indexes. These are these kx, ky. I think it is more clear here. Kx, ky. The indexes. I can compute a lot of things. So for instance, I can compute omega. So I can associate these are indexes. Okay, so I can always compute this thing. I can always compute beta, that is the r whose tangent is this ratio. So this is nothing more than putting the indexes in polar form. Okay, so this is the polar form, my indexes. And then I can recover the indexes from the polar form. But now I can also define period. Okay, so if this is a complex exponential, it must oscillate, and there must be a distance between period. So this is my distance. Here is n divided by omega. And here, for simplicity, we have assumed that the number of rows and the number of columns are the same, and they are equal to n. Okay, and now my complex exponential looks like this. A little bit complicated, but it is the same that we had before. And now if you take real part, imaginary part, you have, as before, you have a cosine and a sine. And I think it is useful to have a look at it. Okay, so you have a cosine, so that means that you would have a periodic signal. And for instance, let's say, what is the amplitude of this periodic signal? So it is, you are multiplying this cosine by something. So that is what is the difference between the maximum and minimum value. So you can make it larger or smaller. You can also, we defined before lambda. Okay, so lambda was this thing. Lambda was this ratio. here, and omega was just the polar or the radius of our indexes. So lambda, the meaning of lambda is the distance in space between a couple of maxima, or between a couple of equivalent points. So the distance between two minimum points, two minima, is also lambda. And because we have now two frequencies, so we have these two frequencies. So we have a frequency in x, so this is omega x times x, and omega y times y. So we have a couple of frequencies, and by changing theta, what I do is to turn this complex exponential around. Okay, so I can turn it. This is something new that appears in 2 dimensions, because in 3 dimensions, in 1 dimension, I cannot do that. So I have only one kind of sign. But now, because I have two frequencies, I can turn this around. And I have a phase shift. So I have, what is a shift in a phase shift in 1 dimension? So let's say that you have a cosine. Like this. So let's say that you have a cosine of omega t plus p. And you make p equal 0. What you have is a cosine. This is the axis, this is family, and this is with phi equals 0. Let's say that now I do phi equal different from 0. So I do, I don't know, phi equal 5/6. So then it is delayed. So then it will start a little bit later. So this distance here is determined by phi. It is not phi. It is determined by phi. It is not phi. Okay, so when you change phi, what you're doing is shifting this around. And thing that you are doing with a complex exponential. So in a complex exponential, if I add a phase term, then I'm shifting my cosine. So if phi is 0, phi 0 means that the maximum is at the origin. If phi is different from 0, then the maximum goes away. But it is the same as in 1 dimension. So when we do the Fourier transform. So okay, so you do the Fourier transform. So you have an x, and you do the Fourier transform. And you have x of k omega. And we said in general, this is complex numbers. And in general, this is a real value function. Okay, I can draw x of t. Draw x of t very easily, so I can do whatever your signal is. You cannot draw complex numbers, so that is why we typically make this kind of plots. So what is the amplitude of it? Then we normally always say it looks like this. Okay. You are familiar with this kind of representations because these are complex numbers. You cannot represent complex numbers. You can only represent real numbers. So you represent the amplitude, for instance, and you also can represent the phase. So you represent the phase of this. And then it looks like whatever it is. Actually, it has to be symmetric. And so it has to be symmetric, I will make it symmetric. All right. Okay, so let's make it symmetric. So let's say it is like this. Now it is symmetric. Okay, this one is incorrect. This one is incorrect. Okay, you can also represent the real part if you want. The real part of X of A. You can also represent the imaginary part of X of A. You can take the complex number and represent whatever part you want, but you cannot represent the complex number itself. Here, do the Fourier transform, and you take this image, you make it gray, and now you represent the Fourier transform. And the Fourier transform is complex, so I can represent the real part and the imaginary part. And then I will also have my frequency axis. So here, look at this. Here, what we are saying is this is my frequency axis. This is my origin of my frequency axis. These are low frequencies. These group ones are high frequency. So this is high frequency, and so on. So you can do the same now, but now in 2 dimensions. In 2 dimensions, these are my frequency axis. This is low frequency. As you go away from the origin, you have high frequency. So it is all the time the same. And you can represent real and imaginary parts, or you can represent amplitudes and phases. Okay, so this one here. So you can represent amplitude and phase. Yeah, power spectrum. Sorry, power spectrum. It will be a little bit more general than it is. So power spectrum is, how do you define the power spectrum? You have a signal.
I have a question.
Sure.
In the slides that you put before,
This one.
on the one with the image, that one. I don't understand like how, if you, like the one with the real and imaginary part, I don't understand how when you like combine those you get like boundaries.
You combine these two and you get this one? No.
Like no, the original or no.
The original image. So this is the Fourier transform. So if you add these two, just by adding by any means, you don't get this one. If you want to recover this one, you have to apply the inverse Fourier transform. So each one of these, so for instance, let's look at the particular one. So let's say this coefficient goes with this one. So this is the real part, this is the imaginary part, and this is a complex number. And then I have to make this sum. You see that we have somewhere. We had a, I don't remember where. Here. If I want to recover those real and imaginary parts, is this number. And I have, this is a complex number. I have to multiply by this complex exponential. So this complex number by this complex exponential that looks like this oscillatory thing gives me an oscillatory thing that has this amplitude and phase. And I have to add all these images, and then by adding them, you get the original. Okay. So the information is the same, but it is somehow encrypted. Yeah, Maria. That's a very good question. So the color, we have explained this only for scalar images. So if you have R, G, and B, now you will have 3 Fourier transforms, one for R, one for T, one for B. Okay. Or we already know the value, for instance, of the luminance. So you go from this image to the luminance, and then this is the Fourier transform of the luminance. So the Fourier transform is only defined for scalar images, not color images. Okay, good. Then the power spectrum. Okay, so let's say that we have a signal X of t. I'm sure you have seen this thing, and you may not remember the signal. x of t, that is a random signal. In general, let's say it is a random signal. So what does it mean that it is a random signal? So you observe it once, you get this thing. You observe it another time, you get now this thing, which is kind of similar, but it is not exactly the same. So every time, these ones are called realizations. If you have a random signal, every time you observe it, you get something different. Typical thing is noise, right? Okay, now, how do you define the power spectrum of random signal? So power spectrum of X is what? Do you remember that? You don't remember. It's something that depends on spectrum, means frequency. And it was the Fourier transform, of the autocorrelation function of X. Do you remember that? X. Now we have this axis here is called the lag. Do you remember the definition of autocorrelation? The autocorrelation was, this is a Fourier transform, and now the expected value of X of t times X of t plus X. Okay, so this is closing the expectation and this is closing the Fourier transform. Okay, so yeah, this is for random signals. What if my signal is deterministic? So I don't have realizations. Every time I look at it, I get the same image, always the same signal. Then this is simpler. So this is simply x j omega squared. So you do the Fourier transform of your image, you take the amplitude and you square it. And it depends on frequency. That's the right dependence. And it is this kind of plots that we typically do. So the power spectrum, they look like this kind of things. So typically you have more energy at low frequencies and less energy as you walk away. Okay, now we have images and we have Fourier transform. So I can find the Fourier transform, the power spectrum of my image. So it is the same. So I will assume that it is deterministic, and then it is simply the Fourier transform module squared. Yeah.
Can you give us an example of random events?
Noise. Have you looked at the TV? No, there are no TVs with this. But have you seen the noise of TV? That is just very random points, white and black, and it looks great. That's noise. And let's look at an example here. What is this one? I will come back to that later. So noisy image. Noisy image. So, and this happens. These things are exaggerated. Okay. Well, they are exaggerated and not. Okay? So typically you don't see images in your cameras like this. That is an exaggerated noise. But this kind of noise exists in the camera. It's much smaller. It exists. So that means that the signal that you see is not completely deterministic. So if I take a couple of pictures of you, the values that I get are not exactly all the time the same. They have random fluctuations. And for instance, there are domains, and this is what we work in at the CSIC in my group. So what we do is hopefully can see sign is like this. Yeah. So yeah, this is an example of it. So you see all these small spots. All these spots, they are proteins. And the signal to noise ratio there, it is 1/100. So you have 100 times more noise than signal. So your proteins, they look very much, they're embedded in a lot of noise. So it is like the example that it was exaggerated before, but even 100 times that. So you have 100 times more noise than signal. Okay, then yeah, we can define power spectra, and this is important. So this is the uncertainty principle. So the uncertainty principle actually it is very much. It is something that probably you know. Okay, so let's say I have x of t, this is t, and I have a delta function here. So this is my signal. I do the Fourier transform. What is the Fourier transform of this? How does it look like? I will only draw the amplitude because I'm not able to draw the complex numbers. And how does it look like? What is the Fourier transform of that? Is this thing, right? Omega times no, isn't it? It's this thing. So what is the amplitude of that? It's flat. It's 1. Okay, let's look at another example. Now I will do it. So we have a cosine. We have a cosine here. What is the Fourier transform of that? What is that? Two deltas. Okay, so let's put labels now. So what is the support? So the support is of this function. So the support is what are the values of time for which the function is different from 0. It's very small support. It's very, very small. So this is very compact in real space. What is the support in Fourier space? It is infinite. It's infinite. And what about this one? What is the support here? It is infinite. What is the support here? It is very compact. So that means that you cannot, for instance, if I ask you at which time do you have energy in this signal? You know it very well. I have energy here. You know exactly. You are very, very precise about the time where you have energy. At which frequency you have energy? All frequencies. Now this signal. At which frequency you have energy? You are very precise. Only these two frequencies you have energy. At which time? Now you are totally precise. So at all times. So you cannot constrain energy to be compact, both in real space and in Fourier space. Actually, there is a relationship between the two. So let's say that you have now a faster cosine. So we use different colors for this. You have a much faster cosine. So you have some cosine like this. Where should it go in the Fourier transform? Now this is always put labels, okay? So always put labels on your axis, so I should also do. This is x of t, this is t. Okay, so where should this go? Farther. This is high frequency. This is high frequency. What if I have a much slower frequency? I have this cosine. Where should it go? It should go here. So now if I look in terms of support, kind of extended support, this support is small. This support is much bigger. So if something is very quick in time, it goes to very high frequency. So the support here is much larger. And if something is very compactly supported in Fourier space, then it is much smoother in frequency. Okay, and yeah, so this is the uncertainty principle. So you cannot be compact in both spaces at the same time. And there is a lower bound. That means that you cannot be more compact than something that depends on what is your supporting frequency. What is your supporting real space cannot be smaller than something. That is called the uncertainty relationship. And actually, this is related. Have you heard of the Heisenberg uncertainty principle? Heisenberg. Principio de incertidumbre de Heisenberg. This is related to this. So this is the signal equivalent of that Heisenberg thing in physics. And here you have this idea. So if you have a couple of deltas, then what you have in this is frequency. So what you have in real space is this sign. And now let's look at this. So now I have a couple of deltas in one direction. So in one direction I have a couple of deltas. In the other direction I'm completely flat. So completely flat, you know, from this example, we have it here. Completely flat in frequency or in one domain means a delta in the other domain. So if I'm flat in one domain, now in frequency, I have a delta in the other one. So now, because I have two directions, so I can be completely determined in one direction, but completely undetermined in the other one. So I have a sign here, by this multiplied by a delta function. So now you can be compact in one direction, infinite in the other direction.
Could you repeat the first one?
Sorry?
The first one. Could you repeat that?
That one. This is a couple of deltas. This is a couple of deltas, so it is a cosine. And this couple of deltas means you are infinite in one direction and infinite in the other direction. So that is why. Also, this infinite in this direction, we are at zero frequency. So this is the origin. So this is zero frequency in this axis. So that means zero frequency means a constant. So zero frequency, you have a constant value here.
And in the other case, there was a...
This is constant in frequency, so it is. So that means this is the equivalent of you are a delta in time. In this direction, I'm a delta. So that means that in the frequency space, I will be flat.
See, I don't understand. There are in frequency we have there two deltas, and in space we have there one delta.
Here, this one. This one doesn't go with this. This one goes with this, and this one goes with this.
But why in that case deltas are 2 points, and in that case a delta is a line.
But here we don't have a delta.
No, that is a cosine. You see?
That is a cosine. Yeah. So in real space, here we have a delta, here we don't have a delta.
Sí, pero me
So-
refiero, ¿cómo sabes que esto de abajo es una delta? Porque
Este,
sí.
porque es 0, 0, 0, 0, 0, algo, y luego 0 otra vez.
Ah, vale, vale.
Y se comportan igual, fíjate. Esto es una delta en un espacio, en el otro espacio tiene que ser una constante. Aquí que tengo una delta, esta vez la tengo en frecuencia, luego en el otro espacio tiene que ser una constante. What about this one, for instance, here? So here, in this direction, we have a step function. So in 1D, we would see this kind of spectra. So in one direction, in this direction, I should see this spectra. So these are the peaks of this Fourier transform. And in this direction, I'm almost flat. So flat means constant. So in this direction, I should have a delta. And then this is some things that I don't want to enter now. Very specific to the Fourier transform in MATLAB. And I think we will leave this for the next day. So, all these reasons of what are the different indexes, different frequencies, and all this. So we leave this for the following day. And that's all. Yeah.
Can you go to the other page? Yes.
Yeah.
It depends on the axis.
Depends on the axis, yeah. So let's say that I turn this 90 degrees, then this would also turn 90 degrees.
So if you are looking in this axis, it is a constant, you said, no?
Yeah.
But if you look in the other axis, it's a delta.
Yeah. So in this direction, it behaves as a constant in real space. So that means that in this direction, the Fourier space has to behave as a delta. In this direction, it behaves as a step. So in this direction, it should behave as this kind of load.
But in this direction, why is not a delta?
This one is not a delta, so it is larger than a delta.
Okay.
You see, it has a few samples, not just one. So in this direction, it should behave as a sink. So in this direction, it should behave as a sink. Very good. Bueno, vamos a hacer el examencillo antes de que se me acabe el tiempo. Eso está aquí.